Okay, so this slide is talking about sampling distribution of X bar when your sample size is large. Okay, so central limit theorem. The central limit theorem is actually the summary of what we've done in the last slide. Remember that we were looking at the stat key in the Major League Baseball, and we were kind of looking at how the distribution of X bar, sampling distribution of X bar changes when sample size is equal to 10 and 50 and 100. And we kind of noticed that as sample size increases, the mean of the means stays about the same as mu, and the standard deviation of X bar actually is getting smaller in the rate of sigma over square root of n. And also the shape of the distribution as sample size get larger, the distribution of X bar get more closer to a normal distribution. So we can kind of summarize that idea in one sentence, and this slide pretty much is what it is. So suppose a random sample of size n is drawn from population with a sufficiently large n. Your distribution of sample mean X bar is approximately normal distribution, no matter what the population distribution of X is. So in other words, your X bar, so sample mean, if it's not X, that's actually an important part of it. Your X bar sample mean approximately follows normal distribution with the mean of X bar, same as mu, and sigma of X bar, standard error of X bar, is equal to sigma over square root of n with sufficiently large n. Okay, so there are three components once more: the mean, standard error component, and shape of the distribution. Okay, so now we know this is actually a pretty powerful theorem. So what we're saying is no matter what your original distribution is, your sample mean with a sufficiently large n, your sample mean, you can assume that will be approximately normal. So any of the probability that is related to your sample mean, you can pretty much calculate it using normal distribution idea, which is in chapter 7. Before we actually look at the example, I want to kind of point out that what do we mean by sufficiently large? Is 20 sufficiently large? Is 50 sufficiently large? Is 100 sufficiently large? The actual answer is actually depend on. However, in general, we call our magic number is about 30. So in general case, unless it is really extreme, about 30 sample size will be large enough that your X bar will be approximately follows normal. And again, it depends on your population distribution is. For example, remember that when your population follows normal distribution with real small sample size, even 1 or 2, your X bar will follow normal distribution. If your population distribution is really far away from the normal distribution, it will take a little longer it will probably take a little longer than 30 for X bar to be approximately normal. So it actually depends on. Okay, so examples. So how we're going to use the central limit theorem, how we're going to calculate some probabilities for X bar. To talk about it, suppose for the population of Truman students, the mean amount of sleep gotten the night before is 8 hours, and the standard deviation is 2 hours. So suppose that's true. So we can kind of summarize that. The population random variable X here is amount of sleep night before, and expected value of X is 8, and standard deviation of X is equal to 2. So we kind of summarize it right here. So here's the scenario. On the final exam day of my Stat 190 class, I asked student, hey, how long did you sleep last night? I have about 35 students in the class, and they answer whatever the amount of sleep they took last night, and I calculated average, and it was 7.16 hours. Is this unusual enough that I can say that they slept less than usual on day before the final day? So we can actually calculate it. So how we're going to approach that is we're going to calculate this probability that X bar is less than 7.16. The whole idea is if this is pretty big value, that means you're going to see 7.16 pretty often when your mu is equal to 8 and sigma is equal to 2. If this is really small value, the probability is really small, that means it's really rare case that you will see 7.16 or less slip if actually mu is equal to 8 and sigma is equal to 2. So here is the summary of it here first. Your X bar here is the mean hour of sleep of a sample of 35 students. Oops, sorry about that. Where's that? That was a typo. So 35 students there. Okay, then your expected value of X bar is 8, and your sigma of X bar is 2 over square root of n, your sigma over square root of n, so it's actually this value. By the central limit theorem, you can say that X bar is less than 7.16 will go just like X minus mu over sigma over square root of n. The only difference from before, from chapter 7 is instead of we're using sigma at the bottom, we'll be using sigma over square root at the bottom because we're talking about distribution of X bar. Not only X, we don't actually know what the X distribution is here, right? But we know that X bar distribution is actually normal distribution. So here at the bottom will be the standard error or standard deviation of X bar goes down there. So will be sigma over square root of n goes down there. Okay, so if you calculate this term, will be negative 2.48. And if you look up the table, Z table, here I'm going to show you a Z table, negative 2.48 right there. Right? So will be 0.0066. So 0.0066. So less than 1%, 0.6% of the time you will observe this value. So is this rare or is this common? It's actually a pretty unusual case, right? So again, using central limit theorem, we can calculate this probability and make some kind of story out of our data set. Okay, then next question related to the previous slide. Without calculation, the probability X bar is less than 7.16 based on the sample size of 100 be smaller or larger or the same. So the whole idea is everything stays the same except your sample size is not 35 anymore. But apparently I have a bigger class and that class size was what? 100. Then what's going to happen to this whole probability? What do you think? Well, the bottom line is if n is large, this value will get smaller, and then this whole value will get larger. Right? So then the probability the X bar is less than 7.16 will be more like a bigger standard deviation away from the mean. So your probability will get smaller. It will be actually bigger negative value. That this whole thing will be a bigger negative value, which will result your probability be smaller. Okay, so to change a gear, This is another example, but we're gonna look at that Major League Baseball salary data set one more time. And there are, I'm trying to write down 3 different kind of scenarios you can actually think of. The first 2 are kind of similar question. What is the probability that the mean salary of randomly selected 100 MLB players is larger than 5.5 million? Same questions, but the first one, use central limit theorem. So, calculate the probability by hand, just like we did in previous slide. The second one is answering the same question, but using empirical probability. And I'm going to talk about that a little bit more in a couple of slides. It's coming. The third one is actually problem itself is a little bit different. What is the probability that the salary of a randomly selected 1 MLB player is larger than 5.5 million? So 1 and 2 we're talking about the mean salary of 100 players, and the number 3 is actually talking about individual salary. So that will be a little different here. Okay, so the first approach, what is the probability that the mean salary of randomly selected 100 the MLB player is larger than 5.5? So I got this information from Stacky. So remember, we're gonna go back to Stacky here. Where's my Stacky? Where are you? Here we are. Okay, so Stacky, baseball, this is the data set. Okay, so remember that. So the mean of the salary was 4.215 once more, and standard deviation was 5.481. Okay, so I just copied it there. The 5.481, but since we're talking about the sampling distribution for X bar, you can calculate the standard deviation of X bar or standard error of X bar by sigma over square root of n, and it happened to be 0.5481. So by the central limit theorem, again, X bar is approximately normal. Why can we use the central limit theorem here? And again, our original distribution was very right skewed. It's far away from normal distribution. But our sample size is 100. So when sample size is large, sufficiently large, your X bar can assume to be approximately normal. So we can actually use central limit theorem here. So probability X bar is larger than 5.5 is, so you transform your X bar to the Z. But when you do that, you subtract your X bar value, your mu value from the X bar value, and divide it by your standard error of X bar here. If you calculate this value, it will be 2.34. And if you look up 2.34 on the table, 2.34. Well, so it actually is same as negative 2.34 or less. So you will see 0.0096 there. So here is your 0.0096. So that's one way that you can calculate this probability. Second one is the same thing, same question, but we can also find it using the empirical probability. And to do so, we're actually going to use the stat key, back to the stat key here. Okay. We're talking about sample size of 100. So I'm going to change that thing to 100. And then I'm going to get a whole bunch of X bars, the samples. And let's say I want to have a couple thousand samples here. And then for this is the empirical distribution of X bar. So every single one of these is X bar. So this one is the distribution of X bar, but this time rather than assuming normal distribution, this is based on actual simulation data set. Well, it happens to be, if it's kind of close to normal, right? But it's not exactly normal. So this is called empirical distribution. So here we're looking for what's the probability that X bar is larger than 5.5. So to do so, we're kind of looking at the larger side. So we're gonna click the right tail here. And then it will, if you actually check the right tail here, it will automatically gives you this number with 0.025 probability. But here, so this number is this probability out of 2,000 times, whatever the number of times it will be larger than 5.312, and that's what the probability is. But what we are looking for is probability X bar is larger than 5.5. So you actually click that number and change it to the 5.5. Then it will give you the probability that X bar is larger than 5.5, which happened to be in this case 0.013. So 0.013 is the empirical probability that mean salary is larger than 5.5. So at this point, so what do you think about these values? So 0.0096, so it's about 0.01, and this one is about 0.013. It's not exactly same, because one was just assuming normal distribution, and this one is based on empirical distribution, but it's somewhat similar. So that's a second way that you can do this. How about then number 3? What is the probability that salary of a randomly selected MLB player is larger than 5.5? Well, for the sake of showing the process, I kind of do this, but I mean, this is actually not the right thing to do, and I will tell you why in a second. But instead of X bar, this time your X, the individual X is larger than 5.5. So you do the same exact thing, except at the bottom will be sigma instead of sigma over square root of n, because we're talking about X instead of X bar. And then you can calculate this probability. To make a long story short, this probability is probably not gonna be a very close one, because your X is actually not necessarily the normal distribution. And in fact, remember this distribution, that's not normal, right? That's actually very, very right skewed. So this probability is actually wrong, and will be very, very off from actual probability. But if X follows normal, you can actually find this process. And I just want to point out that this value is sigma instead of sigma over square root of n. Okay, so this is wrong. I will say that, and then this is the third slide, and we have one more slide to go.